Or not. Are you there? Yeah.
Hello.
Oh, okay.
Yes, I'm here. Hello.
Glad to meet you. Okay, so our last speaker is Jan Stanczuk, who's remotely coming in from Cambridge, I guess. And he's going to tell us how Wasserstein networks can succeed by failing. Thank you.
Hello, can you see my slides?
Yes. Yeah, yes, that's fine.
Okay, perfect. So thank you so much for giving me the opportunity to speak at this workshop. And today I would like to present you the research on Wasserstein GANs, on which I have worked with Christian Ettmann, Lisa Kreutzer, and Carola Schenley. So in this talk, I would like to address two questions. First is, how well do Wasserstein GANs estimate the Wasserstein distance? And the second is Wasserstein distance even the good function, the good loss function for generative modeling? So I would like to start by reviewing the problem with which Wasserstein GANs are trying to solve, which is the deep generative modeling. So the goal in deep generative modeling is to learn a certain high-dimensional probability distribution from a finite set of samples from this distribution. And generative adversarial networks, known as GANs, are one of the most successful approach to tackling this problem. So to visualize how successful they are, here I show a couple samples that came from GANs. So for example, a sample like this face is obtained by first showing GAN a lot of human faces, which are samples considered samples from the distribution of human faces on the space of all possible images. Then the GAN is learning this distribution, and then we can ask it to generate more samples from this distribution. And it outputs faces like this that look very realistic, yet these are faces of people that were not presented to GAN and in fact don't exist. So we can see that the network, the algorithm manages to capture some useful things about the distribution from the samples. Okay, so what are generative adversarial networks? So they have a couple of components. First of all, there is a latent space, which we will denote Z, and a simple prior probability distribution on this latent space, which we will denote as pi. This is usually taken to be just a multivariate normal distribution. Then there is a generator neural network, which maps from the latent space to space X, which is a space in which our target samples live. So this generator network, it takes on the input samples from the prior distribution and then transforms them into samples that look like the samples from our target distribution, which we want to learn. Of course, during training, this approximation of target distribution is imperfect, and we will denote p theta, the generator distribution, which refers to the distribution that the generator currently knows. Then there is another network called the discriminator, and the discriminator takes on the input the samples either from the target measure or from the generator measure. And then it's trying to tell them apart by assigning some real number which serves as a score. Finally, there is a value function which takes the discriminator and the generator and measures their relative performance. And the discriminator is trying to maximize these value functions while the generator is trying to minimize it. So they play in this adversarial game. Here, for example, we have a value function which has been originally suggested by Ian Goodfellow. And in that case, the discriminator just outputs the probability that a given sample comes from the target distribution rather than the generator distribution. And this induces this kind of game dynamics between the generator and the discriminator, and we hope to converge to a certain Nash equilibria where the generator produces the samples that are indistinguishable to the samples from the target measure, and the discriminator always assigns the same score to both samples from the generator and the target measure. So how do we implement this in practice? First of all, we optimize this inner maximum with respect to the discriminator parameter. with this inner loop that optimizes the discriminator. So we sample a batch from our data set from the target distribution and a batch of samples from the generator distribution. Then we calculate the value function and run a gradient ascent step with respect to the generator, discriminator parameters. Then we repeat this process ND times, keeping the generator fixed. And then after ND iterations, we sample again a batch from the target distribution and the generator distribution, and now we do an update with respect to the generator parameters. So this inner loop hopes to compute this maximum, and then we do this. The step with respect to the parameters of the generator to start computing this outer minimum. At least that's the theory. So the classical point of view on GANs is the classical way of understanding them mathematically is indeed assuming that this inner loop is able to find an optimal discriminator. And by this, I mean that this inner loop finds the maximum with respect to the discriminator parameters of the value function. Then we can call this f of theta, and then we can cast the GAN optimization problem as the minimalization of f of theta with respect to the parameters of the generator. And it was shown that under this assumption, the GAN optimization problem can be just rewritten as the minimization of the Jensen-Shannon divergence between the target distribution and the generator distribution with respect to the generator parameters. So this gives us extremely elegant formulation of the GAN algorithm as a certain divergence minimization. Unfortunately, there are problems with this point of view. So it has been found empirically that while we keep this ND, the number of iterations of the discriminator, to be something like 1, then the algorithm works very well. But as we start increasing the number of the discriminator iterations between each generator iteration, the performance actually drops, which is completely contrary to this theory, which assumes that we always find the optimal discriminator between the generator updates. So this one explanation to this has been suggested by Martin Arajowski, where he said that in generative modeling, basically, he pointed out that we are usually dealing with measures which are supported on some low-dimensional manifolds. And if the manifold on which the generator measure is supported doesn't intersect with sufficiently with the manifold on which the target distribution is supported, then as our discriminator approaches the optimal discriminator, the gradients of the value function with respect to the generator parameter will approach 0. So our generator will not be able to learn. And this is caused because by the fact that the Jensen-Shannon divergence cannot handle well mutually singular measures. So if P and Q, if our generator measure and the target measure have disjoint supports, then the Jensen-Shannon divergence will be always equal to log of 2, regardless of how far the supports are from each other. And the same is the case for most commonly used probability divergences. So the idea of Martin Arajowski was to fix this by switching to a Wasserstein 1 distance, which actually decreases smoothly as the supports of the distributions get closer together. So he suggested to replace the value function with this functional that comes from the Kantorowicz-Rubinstein duality formulation of Wasserstein 1 distance. And then since Kantorowicz-Rubinstein formulation requires optimization over 1 Lipschitz functions, he suggested that we should add this gradient penalty term to our loss function, which basically penalizes the discriminator for having norms of gradients higher than 1. And this indeed have looked very promising, as now with this new loss function, increasing the number of discriminator iterations didn't hurt the performance, and actually they managed to report state-of-the-art results with this paper. But I think that we need to be careful here, because the fact that this produced a very good generative model doesn't immediately imply that it has succeeded in computing the Wasserstein distance. In fact, there are three sources of error in this approximation, which should be examined. So first of all, this optimal F is approximated with a neural network. Secondly, these expectations are estimated with Monte Carlo based on mini batches, which arrive to us as we iterate the training of the algorithm. And thirdly, the one Lipschitz constraint is only enforced approximately via soft penalty. In our work, we have examined how closely the Wasserstein distance is actually approximated, but we realized that there is some inconsistency in what people think is the quantity we are trying to approximate. So there are two different estimators of Wasserstein distance that people are interested in approximating, and I will discuss both of them. So the first one we label the oracle estimator. So in this case, we are, and which I think is in line with original idea of Martin Arajowski, we are trying to find the Kantorowicz potential, this optimal F, with respect to the full measure, full distribution, the target distribution, and the generator distribution. But what people also consider in literature is algorithms which accurately approximate Wasserstein distance between mini batches as they arrive during the training iteration. So, and this we label as batch estimator. So that means that at each iteration, when you sample 2 mini batches, you want your loss function to reflect the Wasserstein distance between these 2 mini batches which you have sampled. So we will argue that the Wasserstein GAN, as suggested by Martin Arajowski, fails to compute both of these estimators, and moreover that the second estimator is undesirable. So first of all, the oracle estimator already fails in two-dimensional case. So what we can see here is Wasserstein GAN trying to approximate a two-dimensional Gaussian mixture. The blue dots are samples from the generator distribution, whereas the red dots are samples from the target distribution. And we can see on this logarithmic scaled plot that the loss of the generator is much lower than the actual Wasserstein distance, which I can compute in this case because we are in 2 dimensions. So in 2 dimensions, I can compute the ground truth Wasserstein distance based on finite samples, and the rate of convergence is reasonably good. So I will get very good approximation when I have a lot of samples. We can see that at the end of the training, although the generative performance was very good, the loss of the Wasserstein GAN was 7 times smaller than the actual Wasserstein distance. So that was very inaccurate approximation. And things only get worse as we go into higher dimensions, as it is well known that if you want to approximate one Lipschitz functions up to accuracy epsilon in d dimensions, then you need number of samples that is exponential in the dimension of your space. So if we don't make a prior assumptions on our function, that requires really huge number of samples. And if you're interested in higher dimensional experiments, then I also invite you to read our paper where we discuss this in greater detail. I would also like to recall some classical results about the sample complexity of Wasserstein distance, which show that the Wasserstein distance suffers very heavily from the curse of dimensionality. So in particular, if I'm interested in Wasserstein distance between 2 distributions, P and Q, and then I want to estimate this by taking n samples from P and n samples from Q, and then calculating Wasserstein distance between these 2 samples, then the difference between what I have computed and what I wanted to compute will be very high in high dimensions. And in particular, the number of samples I need to decrease my error up to a certain level increases exponentially as the dimension increases. So to visualize what that means in practice here, I set the dimension of our space of interest to 20 because this has been estimated as a lower bound for a dimension of manifold of human faces. And I've put a standard Gaussian distribution there. So now imagine that I want to, so now the difference, the Wasserstein distance between Gaussian distribution and itself is obviously 0. But if I take n samples from this Gaussian distribution, and then another n samples from this Gaussian distribution, and then I estimate Wasserstein distance based on these 2 batches of samples, then I will get something that is non-zero and actually decreases very slowly with the sample size. So if I want to know, if we want to know what is the number of samples that we need in order to, for our approximation error to decrease to 0.1, this is something like over 10 to 25. And if we want it to decrease to less than 100, then we need more than 10 to 40 samples, which is far larger than any conceivable data set. So there are some fundamental statistical problems here. And there are more arguments against the Oracle estimator. So first of all, this Oracle estimator only makes sense if we are thinking about this optimal discriminator dynamics, but they are not necessarily the right description of what happens in GANs, because original GANs, although they have provably, as proven by Martin Ajarovski, provably bad optimal discriminator dynamics, they worked very, very well when trained with few discriminator iterations. So there is a reason why they worked well, which is not this optimal divergence, optimal discriminator and divergence minimization point of view. Secondly, what I think is very interesting is that adding this gradient penalty term to the original GAN also helps the performance tremendously and removes this problem that the performance drops as we increase the number of the discriminator iterations. So perhaps what is going on is not that we are actually, that Wasserstein GAN computed the Wasserstein distance, but rather that this Lipschitz regularization of the discriminator helped to preserve the balance between the generator and the discriminator and stabilize the training. Because adding this penalty to the original GAN, which has nothing to do with Wasserstein distance, also helps tremendously. And you can see this on these pictures. On the left, we have Wasserstein GAN with the gradient penalty, which performs very well. Then vanilla GAN, which in this case, it failed to capture the Gaussian mixture distribution. But then as soon as you add a gradient penalty to this, it actually performs very well as well, although it has nothing to do with W1. And thirdly, there have been large-scale studies done on different loss functions of GANs, where different GANs have been compared on different data sets and with different architectures and different loss functions. And the finding was that GANs are very sensitive to the change of the neural network architecture of the discriminator and generator, but changing the loss function no of the loss functions consistently outperforms any of the others. So there is no evidence when you look over wide ranges of hyperparameters and data sets that Wasserstein GANs actually outperform original GANs. So the success of Wasserstein GANs may be not due to the good loss function, but carefully chosen hyperparameters and this Lipschitz regularization trick. So that's what I wanted to say about the Oracle estimator. And now I would like to move to this batch estimator. So in batch estimator, we are interested in approximating the Wasserstein distance between mini batches as they arrive in our training iterations. And this has been explored, for example, by Anton Malasto. And he suggested this method called C-transform vegan. So here we can see that the WGAN GP, again, it completely fails to capture the batch Wasserstein estimator, but it produces very good looking samples. Whereas the method of Malasto had very good approximation of Wasserstein distance and had very bad looking blurry samples. So this experiment was done originally by Malasto as well, and he also had these observations. Here we reproduced his experiment in higher resolutions and with state-of-the-art neural network architecture to see if this finding is robust to change in resolution and architecture, and we got exactly the same results as him. So now we have this puzzling question. Why is this the case that a method which has a better approximation of batch Wasserstein distance produces bad samples? And to shed some light on this, it's worth looking at this remarkable similarity between the output of C-transform Wasserstein GAN and a result of a clustering algorithm known as geometric K-medians. So what are geometric K-medians? The geometric K-medians, first, the geometric median, just like the mean is the minimum of a finite set of points of Euclidean space, is a minimizer of the sum of the squared distances. The geometric median is just the sum of the minimizer of the sum of the non-squared distances. And just like the notion of the mean can be lifted to the k-means clustering algorithm, the notion of geometric median can be lifted to the geometric k-medians clustering algorithm. And now with this, we were able to generalized result by Canas and Rosacco, which showed a connection between Wasserstein 2 distance and the k-means clustering algorithm to prove a connection between Wasserstein 1 distance, which is what is used in Wasserstein GANs, and the k-geometric medians clustering algorithm. So what we were able to show is that if you take the distribution, empirical distribution formed by the centroids of k-geometric medians, then this distribution minimizes the Wasserstein 1 distance from the empirical distribution formed by your data set among all distributions with support size equal to k. So since our training data comes in mini batches, if we take k to be equal to the size of the mini batch, that means that the batch consisting of the centroids of the geometric k medians is a batch with minimal 1 Wasserstein distance from the empirical measure formed by your data. This theorem requires a certain refinement, as in practice, when we are training Wasserstein GANs, we are not comparing our mini batches versus with the whole data set, but rather we are also taking a mini batch from the data set and comparing this. So this is room for further work to refine this theorem, but we see that empirically this is also true when you subsample the data set. When you compare mini batches. So in this experiment, we show this empirically. We fix 3 different batches here. The first batch is a batch of real human faces. Second batch is just a repeated face, which has been obtained as the pixel-wise average of 10,000 faces. And the first batch is formed by the centroids of k-geometric medians. Then each of these batches we compare with many batches of human faces drawn from the CelebA dataset, and we calculate the average Wasserstein 1 distance. What we find is that the batch of real human faces has much higher expected Wasserstein 1 distance from other batches of human faces than the other 2 batches. In particular, the batch consisting of k-geometric median centroids indeed has the lowest Wasserstein distance from batches of real human faces. So this has some very big implications for our generative modeling problem, because if you give me 2 generators, one of them is generating real human faces, and the other one is always outputting the centroids of k-geometric medians. If I use batch Wasserstein distance as my loss function, then the one that outputs the centroids will have lower loss than one that outputted perfect human faces. So that means that that's not a viable loss function, and that perhaps sheds some lights on why Malastos' algorithm produced such poor samples. So one might wonder what causes this problem. And this could be, one could think that this is again sample complexity issue. And in our paper, we have we try to control for this by examining entropic regularization. And I invite you to read it if you're interested in this. And we found out that it doesn't fully explain it. And what our conjecture is that the source of the problem here is a very close connection of Wasserstein 1 distance with pixel-wise L2 distance. In fact, if you have 2 finitely supported measures, P and Q, with equal size of support, so we can think about these distributions as 2 batches of images, then the Wasserstein distance between these 2 batches of images is equal to just a sum of pixel-wise distances between images in the first batch and the images in the second batch, except that images in the second batch have been permuted with some permutation sigma, which minimizes this quantity over possible permutations. So that means that the Wasserstein 1 distance is very, very closely related to pixel-wise L2 distance. But the pixel-wise L2 distance is a horrible metric to compare images. And this is visualized in this graphic here. So the first graphic is some reference image. The second column shows, the first column shows some reference image. The second column shows some slightly altered, but semantically and perceptually very similar image. And the third column shows an image which is semantically completely different, yet in L2 distance, in pixel-wise L2 distance, the third column is closer to the first column than the second column is to the first column. So if I'm using a pixel-wise L2 as my measure of similarity between images, then this insect here is closer to this mammal here than this mammal here is to this mammal here, which is of course not failing to capture the semantic and perceptual features of these images. So we believe that in order to remedy Wasserstein GANs, one has to address three issues, which are sample complexity, which could be done by entropic regularization or some kind of sliced distances. One has to replace the ground cost, the L2 cost, by some perceptually meaningful distance. For example, L2 distance between VGG embeddings or something along these lines. And thirdly, one has to address this issue of the approximation of optimal discriminator, possibly by improving the optimization algorithm or by encoding some prior knowledge about the structure of the Kantorovich potential into the neural network architecture. Because if you want to avoid this curse of dimensionality results for Lipschitz functions, we need to somehow encode the prior knowledge about the function we are looking for or restrict the search space. Otherwise, we will just need infeasible number of samples. And that is all I wanted to tell you today. If you're interested, if that talk was interesting to you, then I once again invite you to read our paper, which is available on arXiv now. And I also highly encourage you to read these other two papers, which also cover this topic and have been a huge source of inspiration for our work. And if you have any questions, then I am happy to take them now, or you can email me later under this address. Thank you so much.
Thank you for the wonderful talk. Comments, questions?
Okay. Can you hear me? Yeah, thank you very much for the wonderful talk. I just want to add maybe one more possible explanation why you see that W1 or Wasserstein GAN didn't give you the best image, because I think the entire Wasserstein metric is in the weak side, no matter W1 or W2. If we linearize, it's going to be in the Sobolev space W-1P, that class. So basically, we are using a weak norm. And when you minimize the weak norm to the minimum, you actually have a very flat bottom. And that's why you have a the smaller the objective function, the more smooth you obtain. And we see that all the time in some other applications. So what will improve, make it better, is to go to a stronger norm. So I think the fact that you have this combination, it probably was, you are taking advantage of the W1, the geometric feature, but in the end, because of the error and or the batch noise, that actually push you in the neighborhood of some stronger norm. The L2 actually play a role, and that's why you get a better high resolution image.
Mm-hmm. Thank you. Very, very interesting perspective.
Yeah, thank you also for a very intriguing talk. I would like to somehow understand the following. So somewhere in the middle, you basically were implying also, and I agree, right, that even if you knew the target measure perfectly and you're using an empirical measure and you're pushing it forward, the best thing that you would get is that you're converging to these K medians. And as you noted both kind of on the images, right, is that when you average these images and you obtain the K median, this is no longer on the manifold of images that you would like to be at, because that's really what Wasserstein measures. And, you know, this average is going to be off that manifold. So I'm actually, you know, what is actually puzzling for me is how could it possibly work, right? Even with when I'm making the error, what is that is making this GAN, when it works, to actually produce things on a manifold, which we don't know what this manifold is, and there is nothing explicitly in the modeling that is trying to guess. Thank you.
Yes, so this is a great question, I think. Yes, so this is a great question. So we kind of, the title of the talk is that Wasserstein GANs work because they failed to approximate the Wasserstein distance. So I also think that the original Wasserstein GAN GP, which worked quite well, does not approximate the Wasserstein distance. And the question is, okay, but then since it worked, what did it do, right? I don't think there is a satisfactory theory of this at the moment. I mean, there is, of course, some intuition that you can think that this discriminator just managed to, because if it's not a Kantorovich potential, then it's just some function that assigns a score. It assigns a high score when things look like faces, like if they look like they lie on the manifold, and it assigns low score if they look like they are not on the manifold. And it doesn't, the connection to L2 is not enforced when we are not approximating Wasserstein distance. So I think that this kind of heuristic framework is, it kind of allows it to come up with some more flexible divergence between probabilities, which is learned in a way with this discriminator network. And it's more perceptual because this is a neural network, which this convolutional prior in the architecture of the neural network allows it to capture perceptual features well. And then there is also a good question why it doesn't memorize the training data, right? This is also somewhat mysterious, but this requires, I think, just better understanding of overparameterized systems than we currently have. It's a general question for neural networks, right? Why they don't overfit, although they could. Does that answer the question?
Yeah. Any more? So,
If you have to ask.
okay, we have a public service announcement.
I have a question. So my question is, so you said that in a very good way that you know, if the batch size is small, actually you are computing something else. But so if you increase the batch size, what does it happen? So you still have these artifacts, some, you know, these k-means stuff, or maybe if you, I don't know, I think the batch sizes usually are 16 or 32 or something like that. If you put like 200 or 300, maybe, you know, it gets more complicated and it's not feasible maybe, but what do you get?
Yeah, we tried with something like 500, I believe was the highest I've tried, 512, and you still get blurry looking faces, like looking like k-means centroids. I mean, you could ask a question, what happens when you do like full batch optimization, for example, but that's a really very hard to check in practice, as that would require a huge GPU memory to run such experiment. And I would like expect that it would overfit heavily to the training data in that case.
Let's thank the speaker again.
Thank you.
And I think the public service announcement was that I think the music school has a concert now that maybe people will be interested in, but.
Yeah. So there is a